Hey everybody. Today we're talking about the uniform distribution, which describes a continuous random variable with constant probability density. So we're going to call the interval on which the uniform distribution is defined a comma b. The density function is given by 1 over b minus a. The probability that the random variable lies in a particular subinterval a comma b is proportional to the width of that subinterval. The graph of the PDF always looks like a rectangle. So it has height 1 over b minus a and width b minus a. So the total area is 1, just as you would expect from a legitimate probability density function. The probability that x lies in a particular subinterval, call it c comma d, of a comma b, the interval on which it's defined, is just the fraction of the interval that's covered by that subinterval. I'm showing the integral here. We're integrating 1 over b minus a from c to d, and you get d minus c over b minus a, which is just a fraction of that interval that's being covered. Visually, it's the proportion of the large rectangle that's defined by the probability density function on the support that is shaded between c and d. The expected value of a uniform random variable is just the midpoint of the interval on which it's defined. And the derivation is shown here. We're integrating over the support x f of x dx. So that's just your basic definition of expected value. The support is from a to b. The density function is b minus a. We do our integration, plug in the endpoints, subtract what we get when we plug in those two endpoints. We get 1/2 a plus b, which again is the midpoint of the interval a comma b. To compute variance and standard deviation, we apply the formula that variance is the expected value of x squared minus the expected value of x, quantity squared. So we need to compute the expected value of x squared. Fortunately, that calculation is more or less identical to the calculation for the expected value of x, just with the x in the numerator of the integrand here being replaced with x squared. When we do out all that calculus and arithmetic, we get 1/3 b squared plus ab plus a squared. So now we compute variance using that formula I mentioned a little bit ago. There's some algebra involved. In the end, we get 1/12 b minus a quantity squared. And that means that the standard deviation is 1 over the square root of 12 times b minus a. Finally, let's find the moment generating function of a uniformly distributed random variable. That means finding the expected value of e to the tx, and that means integrating from a to b e to the tx over b minus a. And we need to consider the cases t equals 0 and t not equals 0 separately here. When t is not equal to 0, we anti-differentiate and we get e to the tx over t times b minus a. We evaluate that from b to a, from a to b rather. And here you can see why we have to assume that t is not equal to 0. We have a t in the denominator here. When t is equal to 0, things are simpler because e to the tx is just 1. So we're integrating the constant, 1 over b minus a. When we do that, when we integrate, take the endpoints, plug in, subtract, we just get 1. Putting these two cases together, we get the moment generating function given as a case-defined function. And you can confirm that if you take the limit as t goes to 0 of m of t, you actually do get 1. And that means that m of t is continuous. And in fact, you can confirm that this moment generating function is actually infinitely differentiable at t equals 0. And that's helpful because it means that you can use it to compute the moments of the uniform distribution. It's an alternative way to do that. I recommend doing that for practice to verify that the expected value is actually given by 1/2 b a plus b, which we found earlier, and also to verify that the variance is given by 1/12 b minus a quantity squared.